In this video, I will apply Kirchhoff's loop rule on an RC circuit where I discharge the capacitor. I have a capacitor charged, C is the capacitance, R is the resistance of the resistor, and the red arrows indicate the direction of the electric field in the circuit. It points down inside the capacitor and it points down in the resistor. I'm also indicating with numbers 1, 2, 3, 4 some points along the circuit so that I can define the loop. When I apply Kirchhoff's loop rule, I start from 1 and I move clockwise around the circuit and then I come back to point 1. So I have the sum of all the potential differences that should give me 0 at the end. Now I need to get rid of any potential difference where I move along an ideal wire from 1 to 2, from 3 to 4, and the rest are non-zero. Now when I go from 2 to 3, I move in the same direction as the electric field, so I know the potential will decrease, so that will be a minus IR. When I go from 4 to 1, I know I'm moving against the electric field, the potential should increase, so that should be a plus. Now remember, I said before, I know that C, the capacitance, is defined as Q over delta V, and this means that the potential difference across the capacitor is just Q over C, so I can use that here. Similarly, as when I was charging the capacitor, if you use the definition of the conventional current, you're gonna have you will have an expression where I equals dq over dt with a plus or minus depending on how the charge on the capacitor changes and what happens to the current. I'm gonna skip those things for now. The important thing, if you plug the definition of the conventional current in this expression, what you end up getting is a differential equation. And solving differential equations is beyond the scope of an introductory physics class, but what I will do is, so I'm gonna skip the math where we solve the differential equation and I will tell you what the result is. But it is important for you to understand that those equations do not somehow are not obtained by magic. I use the physics ideas that you have learned so far, like Kirchhoff's loop rule, potential difference across the ohmic resistor, the definition of the capacitance, and then I need to do some math that is more complicated for introductory physics than what we would like. So I skip that part and then we obtain the expression for the current as a function of time. And this is what it would look like, minus T over RC. And I have done this graph. We know that the current will decrease exponentially here. So this is I. This is time. It's gonna start from I naught and it will decrease in an exponential way. And then for the charge on the capacitor as a function of time, it's gonna have a similar this function will have a similar form. Remember, here in this circuit I am discharging the capacitor. So now I should see that the charge on the capacitor decreases as a function of time. So this is Q, this is T. At T equals 0, I start with the Q naught and then the charge on the capacitor decreases. If you wait long enough, you should see effectively no charge, absolutely no charge on the capacitor. Now, if you have a problem where the problem is asking you to find the potential difference across the capacitor, then we're gonna say this is just Q over C, and using the result, it's gonna give me Q naught over C e to the minus T over RC. Okay, so the important thing, once you have the charge on the capacitor, you can easily find the potential difference across the capacitor as a function of time if you need that.